All right, so the next kind of preferences we're going to look at are these well-behaved preferences. We'll talk about the general approach to solving these types of problems, and then we'll do this example like we did in class, and hopefully that will help. It's like a numerical one at first, and then it kind of gets a little bit more general down here. All right, so as we kind of talked about before, this is when, for example, it's definitely not a min. This is, for example, when we want to maximize our utility function subject to some constraint, say p1x1 plus p2x2 equals m, and the utility function has like certain form where it's kind of a well-behaved preferences. So an example would be these Cobb-Douglas ones, or to the 1/2, x2 to the 1/2, whatever you want. So this is like an example of it. So, we've learned a few different actually ways to solve these types of problems. Like visually, I think intuitively, one way is kind of easy to see. So here's our budget constraint with the slope of negative p1 over p2. Here's our indifference curve that's nice and well behaved. The solution is going to be this tangency condition, or when the indifference curve is tangent to the budget constraint. And the slope of this indifference curve, remember, is like the marginal rate of substitution, or the ratio of marginal utilities, the negative of the ratio of marginal utilities. And so there's, 3 different solution methods. You can just pick whatever one you want and always use that. The first one is what I'm going to call the MRS condition. So this is using the fact that the slopes of these two lines are the same at the optimal solution, and then also that you're spending your whole budget. That's going to be that technique, and we'll expand on that below because that's the one I'm probably going to use. Well, maybe I'll just say it right here. So this is like 2 equations, 2 unknowns. And the equations, maybe I'll just say A, is that the negative of the ratio of margin utilities, which is the MRS, right? That's the slope of this indifference curve, is equal to the slope of the budget constraint. So that's saying we're at the point where these 2 lines are tangent. And the second one is our budget constraint. That's supposed to be a 2 equals m. So here are 2 equations, and we have 2 unknowns. Again, x1 star and x2 star are the 2 unknowns, and these are the 2 equations, and we can solve for that. Sorry about that. My dog just saw another dog outside, so hopefully it didn't hurt your ears too much. Okay, so that's like the first technique we can use to solve this. Again, like I'm just going to tell you all of them, or at least 2 of them, I guess, just so you are aware of them. But you don't have to know how to do, in my course, you don't have to know how to do all 3. And if you're not taking my course but watching this, your instructor will probably tell you which way they might prefer or something like that. Like lots of times you might use the second technique, the Lagrangian, because it's a more general technique. All right, so the second kind of technique, I don't think I'll even talk about the third, which is kind of this unconstrained idea, is the Lagrangian. And essentially, this is like a more general technique that you're going to see as you continue on in economics, because there's some intuition behind this Lagrangian multiplier we'll talk about in a second. But essentially, this is like a problem where we set up this Lagrangian where it's our utility function. I'll leave it as general, but, minus lambda, and this is our Lagrangian multiplier, p1 x1 plus p2 x2 minus m. And so we're just putting in whatever our utility function here is, like x1 to the 1/2, x2 to the 1/2. And basically, let's give myself a little bit more room here. We take the derivative of this Lagrangian with respect to x1 and set it equal to 0. Lagrangian take the derivative with respect to x2 and set it equal to 0. And then finally, with respect to the lambda, which ends up kind of just being our budget constraint again. and set it equal to 0. And then what we're going to have is 3 equations. I don't know what's happening with my bracket there. 3 equations, these 3 first order condition and 3 unknowns. And 2 of the unknowns obviously are x1 star and x2 star. The other one is lambda, like we'd solve for the lambda here as well. So either of these 2 methods are going to give you the same answer. So it doesn't matter which one you use, and they're all involving taking, these first order conditions. This is just a more general technique to solve these constrained optimization problems that will maybe kind of work in more of a wider, or more widely applicable kind of learning this Lagrangian. Whereas I think this MRS condition is very intuitive from what our consumer maximization problems are saying, which are basically just these slopes are equal and we're spending our whole budget. Where this is just a more general solution technique for these types of problems. The third way is this unconstrained optimization, which is essentially just kind of putting this constraint and rearranging it so like x2 is a function of x1 and putting it into our utility function and then just maximizing with respect to one of the goods. But I made a video on that you can watch if you want. But these are like the 2 really common methods you see in kind of this intermediate microeconomics course. I'm kind of stressing this MRS condition in class. Other instructors kind of just use this Lagrangian a lot. But either of these 2 methods will produce the same solution for this. Okay, so that's the solution, the general solution technique for these well-behaved preferences. Now let's go look at an example and actually, calculate these margin utilities with a particular utility function. I mean, we can solve this with the Lagrangian as well below if that's helpful for you guys. You can just let me know and I can make a video of doing that as well. So this is one we saw in class. Bo Jackson loves playing both baseball and American football. His well-behaved, there you go. It's telling you it's well-behaved. So it's telling you the solution technique you should use is, this f to the 4, b to the 2, where f is the amount of hours he spends playing football and b is the number of hours he spends playing baseball. He gets an allowance of $50 a week, so that's what his budget is. The quote-unquote price of football is $2 and the price of baseball is $2 in terms of the use of equipment. And how much time should he be spending playing football and what about baseball? All right, just gonna give myself some room here. So let's write out what the problem is first. It's to maximize f to the 4 b squared, and he's picking f and b, subject to the constraint where 2 times f plus 2 times b equals 50. The price of, the quote-unquote price of football is 2 and the price of baseball is 2 here. So this is the problem we're dealing with, and we're trying to solve for f star and b star. So we can use either of those, I guess 3 techniques, but the 2 that I talked about to solve for this. I'm going to use the MRS condition here, and like I said, if you want me to solve this with Lagrangians, we can do it as well. You can just try it yourself and make sure you're going to get the same answer. I didn't make a mistake, and you can make sure that you get the same answer using the other method. So the MRS condition. This is the technique I'm going to use. The first one is the fact that margin utility, the ratio of margin utilities is equal to the slope of the budget constraint. So this is the tangency condition. And the second one is the budget. So I'm just writing them down here and then we'll actually, calculate them with these numbers. And the second one is just well, I'll leave it general since I left the other one general. PF times F plus PB times B equals M. This is our budget constraint. All right, so those are 2 equations and 2 unknowns. We just have to just figure out what these equations are. I think the budget constraint we've already done, but we have to figure out, what this actual tangency condition is with this particular utility function and these particular prices. So maybe I'll just do it in green or something like that. So let's talk about what equation 1 is in this scenario. So we got to figure out the margin utility in this case, I guess I should even relabel them as football and baseball to make it easier. F and B. And this, I guess, should be F, and this should be B in this particular scenario. So we got to take the derivative of this utility function, the partial derivative, with respect to F. So we can just use our exponent rule, and we get this. We'll put a little negative outside of it because it's going to be a negative, but we're going to be able to cancel those out. So that's the derivative of our utility function up here with respect to F. Then we put it over the margin utility of baseball, which is derivative with respect to B in that utility function. So that's 2B, 2F to the 4 and B, if I want to leave it in the same order. And we know that that equals negative 2 over 2 in this case, because the price of both football and baseball is $2. So now we need to simplify this. We can get rid of the negative signs really easily, but we got to simplify this. So like F or B is a function of the other one. So we want F or B on the left-hand side and everything else on the right-hand side, and then we can plug it into our budget constraint. So I'm going to simplify this. Maybe I'll just work across the screen this way. So we can see right away, like, get rid of the negative signs, and right-hand side's just 1. 4 over 2 is 2, so we have 2. And let's think about what our other, how we can simplify this fraction. Really what this ends up being is 2b over f equals 1. So hopefully you can see right away the 4 and the 2 just become a 2. And then negative 2 over 2 becomes a 1 just because I'm getting rid of the negative signs as well. And you see that it's f to the 4 on the bottom, and it's f to the 3 on the top, so that's just an f in the denominator. Got f to the negative 1, so just f in the denominator. And b over 2 over b, we can just cancel out one of the b's in the numerator. So it just becomes, instead of b squared, it's just a b in the numerator. Hopefully that, hopefully that explanation is somewhat okay. I know I went through it pretty quick, but hopefully you can figure out that algebra. We can just rearrange this however you want. You can express f as a function of b or b as a function of f. It doesn't really matter. So for instance, we could see right away that f equals 2b, or depending on how your brain works, like maybe you think that b equals 1/2 of f. Like either way works. It doesn't matter which way you express it. But we need to express it like one of these goods is a function of the other in order to plug this into our budget constraint. Okay, so I'm going to use f equals 2 times b. So that's just moving this f over here. And so now our second equation, remember, is 2 times f plus 2 times b equals, and I got to scroll up, our budget is 50. So now what we're going to do is we're going to take our expression for f from this first equation and just plug it in to here. So 2 times 2b plus 2b equals 50. So what's that? 6b equals 50. So b equals 50 over 6. This is our b star. I'll put it green around it to show it's an answer. And we also know that f star is just 2 times b. So right away we can figure out what f star is. Just going to give myself a little bit more room. So in that case, f star, sorry, touchscreen is a little bit off. So now our f star is equal to 50 over 6 times 2, which is just 50 over 3. So this is our solution. This is our optimal solution, and you'd get the solution whether you use Lagrangian, unconstrained, or this MRS condition kind of technique. Okay, 2B, and maybe I'll just end at 2B because like C is just a little bit more general, and I'm going to maybe do that in another video, just so it doesn't get too long here. But 1B is basically just drawing this solution and carefully labeling the points. So I can do that. We have our answers up above. So let's say F is the x-axis and baseball is the y. We know that the price of each of the goods is $2 and the budget's 50. So the slope of this budget constraint is -1, -2/2. If you just played baseball, I could do 25 hours of baseball. If you just did football, I could do 25 hours of football. Because its budget's 50 and they cost $2 an hour. And then what we did is basically solve. We have this nice smooth indifference curve, and smooth, I know my drawings are never the best, but here's our tangency condition. This is F star here. Oops. And we solve for it being 50/3. And here is B star, and we solve that as being 50/6. This is essentially the problem that we just solved. Okay, so hopefully that's helpful to see the solution techniques for these well-behaved preferences. So it's really, either using this MRS condition or the other way I'd suggest is this Lagrangian. If you want to learn this technique that's going to be used in, your upper level microeconomics theory courses, it's probably going to start using much more the Lagrangian. And we just did a numerical example where we actually solve for that. So what I'll do is I'll make another video where I kind of do a general solution where instead of getting actual prices and budgets, we can solve for this. So F star and B star are a function of prices and income. That's kind of just a more general solution where we can derive the demand functions. But that's, coming up shortly when I find some more time to make a video.